Hello everyone. Today I want to introduce our work, pyKT, which is a Python library to benchmark deep learning-based knowledge tracing models. This work has been accepted by NeurIPS 2022, track on datasets and benchmarks. So what is knowledge tracing? Here is a student's historical learning interactions about the questions and the related answers. Each question is associated by a set of knowledge components. For example, for the questions in the slide, fill in the blanks to make the calculation correct. 16 minus the square of -3 equal to what? The related cases include power, negative numbers. By a series of practicing, the student improved his mastery states about these cases. So, knowledge tracing is the task of using students' historical learning interaction data to model their knowledge mastery over time so as to make predictions on their future interaction performance. Such predictive capability can help students learn better and faster when paired with high-quality learning materials and instructions, which is important for building next-generation smart and personalized education. Recently, due to the rapid advances of deep neural networks, many KT datasets and DLKT models are developed for modeling students' mastery of cases, and they are achieve promising results. However, most existing work only provides cross-evaluation, and contributing factors leading to the success of DLKT still remain somewhat unknown. Moreover, evaluations of existing DLKT work are not standardized, and the reported AUC results of the same approach on the same dataset vary surprisingly from 0.709 to 0.86. Therefore, there is a substantial need for a standardized DLKT benchmark platform, which ensures the methods can be compared with a fair and transparent manner. We designed pyKT, a 5-grade Python-based benchmark library that brings us closer to the requirements of real-world KT applications in educational contexts. We attempt to provide answers to the following research questions. The first one is, what is a reasonable, reliable, and realistic evaluation process for DLKT algorithms? The second question is, how do different characteristics of student data, model design, and prediction scenario affect the model performance? In our work, we survey existing DLKT-related publications in top AI and machine learning venues from 2015 to 2021, and we selected the most frequently mentioned DLKT baselines as our representative DLKT methods. These methods can be categorized as deep sequential models, including DKT, DKT+, and so on. And DKVMN is a classical memory-augmented model, and ATKT is an adversarial model, and GKT is a graph-based model, and AKT, SAKT, Chen are attention-based models. For these models, we select 7 widely used datasets to evaluate their performance. To effectively learn and fairly evaluate the DLKT models, we train the DLKT models on KC response data, which is generated from question response data by expanding each question level interaction into multiple KC level interaction when the question is associated with a set of cases. And we first use the learned DLKT models to predict the above expand KC response data, and then we output the final question level predictions by aggregating predicted mastery levels of its cases. To make the benchmark close to the real application scenario, we divide our prediction scenario into two sections. The first one is one-step ahead prediction, which only predicts the student's response on the last question given the student's historical interaction sequence. And the second one is multi-step ahead prediction that predicts a span of student's response given the student's historical interaction sequence. After extensive experiments, we have the following observations. The first one is attention mechanism greatly affects the DLKT model's performance. The DKT model that first applied deep learning into the KT problem is still superior. The second is one-by-one evaluation on expand KC sequence caused label leakage problem that led to performance inflation. And we also find that DLKT models behave differently for students who have very long interaction sequence. And we also observe that prediction results of different ways of KC aggregations resemble each other, and the late fusion average is slightly better compared to other approaches. As mentioned before, except for prediction scenarios in one-step ahead prediction from observation 1 to 4, we additionally use multi-step ahead predictions, which are also very important from educational scenarios. And there are two different approaches, accumulative prediction and non-accumulative prediction. The accumulative prediction uses the last predicted values for the current prediction, while the non-accumulative prediction predicts all future values all at once. And we found that the choice of accumulative or non-accumulative predictions vastly influence the DLKT performance in the multi-step ahead prediction scenario. In the future, we will add more DLKT approaches and diverse datasets, and we will explore new DLKT opportunities to our pyKT. In general, we propose a Python library standardizing previous efforts in DLKT research that standardize data pre-processing components, and we attempt to meet the requirements of real-world prediction scenario formulation. And here is the website of our work. Welcome to visit. That's all. Thank you.